We saw in our previous video that a moment is essentially the turning effect of a force, and we can calculate it using the simple equation where moment equals force multiplied by distance. In this video, we are going to explore how this fundamental concept applies in practical contexts, particularly in the use of levers and gears. Levers come in many different forms, and even if you've never studied them in a physics class, you've almost certainly used them in real life, perhaps without realizing it. What all levers have in common is that they are used to transmit the turning effect of a force from one location to another. In each case, we apply an input force at one point, and as a result, we get an output force somewhere else. There are two important observations we can make here. First, if the input and output forces are applied on opposite sides of the pivot point, as in the case of a pair of scissors, then they will act in opposite directions, with one acting upwards and the other acting downwards. On the other hand, if both the input and output forces are applied on the same side of the pivot, such as in the case of a wheelbarrow, then both forces act in the same direction, and in this example, they would both be acting upwards. Another critical point to observe is that the output force tends to be closer to the pivot point than the input force, and this design feature means that the output force is generally larger in magnitude than the input force. This principle forms the basis for the usefulness of levers. Essentially, levers enable us to achieve a large output force using only a relatively small input force, which is incredibly helpful in many real-world situations. To understand how this works in practice, let's imagine a scenario where we want to lift a large and heavy rock that has a mass of 200 kilograms. Since weight is calculated by multiplying mass by gravitational field strength and using the approximate value of gravitational field strength as 9.8, this rock would have a weight of 1,960 newtons acting downwards. If we were to try lifting this rock directly without any mechanical help, we would need to exert an upwards force greater than 1,960 newtons, which is far beyond what most people are capable of. However, if we place a solid object near the rock to act as a pivot and wedge a long and sturdy plank between the rock and the pivot, we would effectively have created a lever system. Suppose the distance from the pivot to the rock is 0.4 meters. We can then calculate the moment caused by the rock's weight by multiplying 1,960 newtons by 0.4 meters, which gives us a value of 784 newton meters. This moment acts in the anti-clockwise direction around the pivot. Our goal now is to create a clockwise moment that exceeds 784 newton meters in order to lift the rock. Let's assume the person pushing the lever is only capable of applying a force of 400 newtons. We then need to calculate how far from the pivot that person must push in order to generate the necessary moment. To find this required distance, we rearrange our original equation so that distance equals moment divided by force. Plugging in our values, we divide 784 by 400, which gives us 1.96 meters. This means that as long as the person applies their force at a distance greater than 1.96 meters from the pivot, they will be able to lift the rock, even though their applied force is significantly smaller than the rock's weight. Now let's move on to another mechanical system where moments are key, and that is gears. Gears are found in all kinds of machinery, including bicycles, clocks, and most importantly, cars, and they serve to transmit turning effects from one part of the system to another. Although actual gear systems in machines are often complex and contain many interlocking gears, we can understand the basic concept by imagining a simple system involving two gears. Let's say gear A is connected to the engine of a car, which provides it with a turning force, causing it to rotate. Gear B, on the other hand, is connected to the car's wheels, meaning that if gear B rotates, the wheels will rotate as well. Because these two gears are interlocked, when gear A rotates, it causes gear B to rotate too. This setup effectively allows the turning effect produced by the engine to be transmitted directly to the wheels, facilitating motion. That is, the engine rotates gear A, gear A then rotates gear B, and gear B finally causes the wheels to turn. There are two crucial observations to make about this gear system. First, the two gears rotate in opposite directions. So, if gear A is rotating in an anti-clockwise direction, gear B will rotate in a clockwise direction. Second, the gears differ in size. In this simplified example, the radius of gear B is exactly twice the radius of gear A. This difference in size has a significant effect on the turning force. Specifically, the turning effect or moment of gear B will be twice that of gear A. This means that as the turning force is transmitted from the engine to the wheels, it is effectively doubled. Another important detail is that for every single rotation of gear B, gear A must complete 2 full rotations. So even though the turning effect is amplified, the amount of work done remains the same because gear A has to rotate twice as often to achieve 1 rotation of gear B. This conservation ensures that energy is not created or lost, but merely transferred and transformed within the system. That wraps up everything we needed to cover in this video. We hope this explanation has made things a lot clearer, and we look forward to seeing you again soon.